In this video, we're going to be looking at the photohalogenation of alkanes. Photohalogenation simply means that you're halogenating an alkane in the presence of either heat or light. So if we look at a very simple reaction of methane with chlorine in the presence of heat or light, I can essentially substitute, this is a substitution reaction, I can substitute a carbon-hydrogen bond for a carbon-chlorine bond. And I get essentially four possible products, right? So I can get monochlorination to produce methyl chloride, dichlorination to produce dichloromethane, trichlorination to produce chloroform, and tetrachlorination, removing all of the hydrogens, to produce carbon tetrachloride. And as a matter of fact, this is industrially the main way that we can make carbon tetrachloride, adding a huge excess amount of chlorine in the presence of methane, and you get this liquid carbon tetrachloride as a solvent that's often used. So we're going to look at the mechanism, and of course we're not going to look at the mechanism of the tetrachlorination. We're simply going to look at monochlorination. So methane reacting with one equivalent, essentially, of chlorine to produce methyl chloride and hydrochloric acid. And if we draw the Lewis structures of the reactants and products, we see that if we're looking at this entire reaction, right, methane plus chlorine going to methyl chloride plus HCl, we see that in essence there is a carbon-hydrogen bond that breaks, a chlorine-chlorine bond that breaks, and then what forms is a carbon-chlorine bond and a hydrogen-chlorine bond. And if we look at the energetics of this reaction, we see that to form a carbon-chlorine bond, 351 kilojoules of energy would be given off. To form a hydrogen-chlorine bond, 431 kilojoules of energy would be given off. But to actually break that bond, break a carbon-hydrogen bond, we're going to need 439 kilojoules of energy. And to break a chlorine-chlorine bond, which is the lowest amount of energy, 247 kilojoules. And so the delta H of this entire reaction simply is the bonds broken minus the bonds made, right? And so because we have to add energy to break the bonds and then energy is released to form the bonds. So if we simply take the bonds broken, add them together, we get 686 kilojoules of energy. And if we take the bonds made and we add those up, 351 plus 437, where that amount of heat is going to be given off, and so it's a negative term, so minus 781, and we add these two terms up, and we get a negative 96 kilojoules per mole of reaction of energy, and so we say this reaction is exothermic. So at room temperature, heat is going to be given off in this reaction. And as a matter of fact, when you do a chlorination of an alkane, you have to be very careful because there's quite a bit of heat given off and it can actually catch fire. In terms of the curved arrow notation mechanism, we can think about what's going on at a molecular level, and of course chapter 12 deals with free radicals, and so obviously this is a radical reaction. So the first step in this reaction we see of the two reactants, chlorine has a very weak chlorine-chlorine bond, right? 247 kilojoules of energy. So if I add enough energy in the form of light or heat, I can homolytically dissociate a chlorine bond. And remember, this is, if I have a mole of chlorine, all I have to do is dissociate a small amount of chlorine to form chlorine radicals. And this initiates the reaction, right? So now I have chlorine radicals present, and those chlorine radicals are, those few chlorine radicals are in a large amount of methane and chlorine gas. And so the second step is that once a chlorine radical finds a methane molecule, I can get hydrogen abstraction. And so we typically show that, right? So an electron, the lone electron on chlorine, pairs up with one of the electrons from a carbon-hydrogen bond. The other electron goes to the carbon, and I form a methyl radical plus HCl. So now I have a methyl radical. Obviously, we know radicals are very reactive. And so in that third step, a methyl radical can then come in contact with chlorine. And so that methyl radical is going to essentially abstract a chlorine atom from the chlorine molecule. And this is energetically favorable because remember that a chlorine-chlorine bond is much weaker than a carbon-hydrogen bond. And so we get the formation of a carbon-chlorine bond, and the other electron goes to the second chlorine, and we produce now our product, the methyl chloride. And again, we are producing a chlorine radical. And so we see that these two steps, step 2 and step 3, are the chain propagation steps, right? So these are happening over and over again, and so you're going to repeat steps 2 and 3. The chlorine radical is going to react with another molecule of methane to produce a methyl radical. The methyl radical is going to react with a chlorine molecule to produce your product plus chlorine radical, and that process repeats and repeats and repeats. Now, interestingly enough, as you add carbon-chlorine bonds, the carbon-hydrogen bonds of that molecule actually weaken because the chlorine is withdrawing electron density, and so the carbon actually becomes more electronegative in a sense, weakening the carbon-hydrogen bond. And so if I start to form a lot of methyl radicals, if I have an excess amount of chlorine, there's going to be an excess amount of chlorine radicals. And of course, I can abstract another hydrogen very readily and produce the chloromethyl radical plus HCl. And then that chloromethyl radical can react with another chlorine molecule and abstract a chlorine. And I produce dichloromethane plus a chlorine radical. So you see that, and this is only if I have an excess amount of chlorine, am I going to start to produce multiple substituted chlorinated products. And of course we could go on and on. I could take that dichloromethane and react it with a chlorine radical, abstract a hydrogen to get chloroform, and then on to carbon tetrachloride. Now, when we look at the chlorination of alkanes, so more complicated alkanes, we see that when you have different types of carbons, so different types of hydrogens, you can get different types of products. So we're simply going to be focusing on monochlorination, so adding one chlorine to an alkane. And in this very simple scenario where I have butane reacting with chlorine, again in the presence of light at 35 degrees Celsius, I can get 1 chlorobutane, and I can get 2 chlorobutane. And the yields for these are, so I get 28% 1 chlorobutane and 72% 2 chlorobutane. And if I think about what's going on in this reaction and why I get the product distribution that I get, there are two factors that I have to consider. The first one being statistical, and then the second one being energetic. So statistically, I have a certain number of hydrogens that I can abstract. That's going to lead to one product, and a certain number of hydrogens that I can abstract that leads to the second product. Energetically, if I'm forming radicals, I know I have different types of radicals. So I can form a primary radical, I can form a secondary radical. And so these have different energetics associated with them. Now, it's easy to think about the statistics, and if I draw methane and I draw out all of the carbon-hydrogen bonds, I see that I have two distinct types of carbon-hydrogen bonds. So at the end I have these primary, these methyl groups, right? So I have 6 primary hydrogens, and then in the middle I have 4 secondary hydrogens. So I can abstract any of these 6 or any of the 4. And so statistically, I would expect to see essentially a 60% 1-chloro butane and a 40% 2-chloro-butane as my product distribution, if statistics were the only thing that mattered, right? So because there are 4 hydrogens, 4 secondary hydrogens to every 6 primary hydrogens, I would expect to see a 40% to 60% product distribution. And obviously that, we don't get that. Instead we get a 28 to 72. And so the question is, well, why is that? Obviously, the secondary radicals that are formed are going to be more stable than the primary radicals that are formed. And we can write an equation to kind of think about what's happening in this process. So if we combine the two factors, we can say that the percent of the secondary relative to the percent of the primary is going to equal the rate of secondary hydrogen abstraction, so this is the energetics, times the number of secondary hydrogens, divided by the rate of primary hydrogen abstraction times the number of primary hydrogens. And so that product distribution is related to both energetics and statistics. Now I'm simply going to rewrite this equation. Right, so percent primary divided by percent, so we're looking at a relative ratio. The ratio of percent primary, secondary, to percent primary is the rate of secondary hydrogen abstraction times the number of secondary hydrogens divided by the rate of primary hydrogen abstraction times the number of primary hydrogens. Now, I'm going to rearrange this equation. Since I know the percentages, I can actually determine what the relative rates of secondary hydrogen abstraction to primary hydrogen abstraction are. And so I get that the rate of secondary hydrogen abstraction divided by the rate of primary hydrogen abstraction is simply equal to the percent of the secondary products times the number of primary hydrogens divided by the percent of primary hydrogen products times the number of secondary hydrogens, right? So in this reaction, the percent of the primary was 72%, the percent of secondary was 72%, the percent of primary was 28%. There are 6 hydrogens that are primary, there are 4 hydrogens that are secondary. And so when I do this math, so 72 times 6 divided by 28 times 4, I get 3.91. So essentially 3.91 to 1. Now what does this mean? Well, essentially this means that for every 1 primary hydrogen that's abstracted, there are about 3.9, so about 4 secondary hydrogens abstracted. Now I can do the same thing for 2-methylpropane, right? So 2-methylpropane has primary carbons and it also has a tertiary carbon. And if I react 2-methylpropane with chlorine, again, same conditions, adding light at 35 degrees Celsius, I get 2 possible products. So I can abstract a primary hydrogen and I get 1-chloro-2-methylpropane, or I can abstract a tertiary hydrogen and I get 2-chloro-2-methylpropane. And if I look at the product distributions of this reaction, I see that there's 64% of the primary hydrogens that are abstracted and 36% of the tertiary. And you might say, well, wait a second, why is there more of the primary hydrogens abstracted? Well, Again, you have to think about statistics. For every one tertiary hydrogen, there are 9 primary hydrogens on this reaction. And so, again, we can look at the relative rate of the tertiary hydrogens abstracted to the primary hydrogen abstracted, and we can use that same equation. So the rate of tertiary hydrogens divided by the rate of primary hydrogens is 36%, so that's the amount of tertiary hydrogens produced, times the number of primary hydrogens, so 9. So notice that those 9 hydrogens, right, are really going to multiply that factor of 36. And of course we divide by 64%, which is the amount of the primary alkyl halide produced, times only 1 hydrogen for that tertiary. And when we look at the product of this, we get a product ratio of 5.1 to 1. And so that simply means that, again, for every primary hydrogen abstracted, there's about 5 tertiary hydrogens that are going to be abstracted. Now, for synthetic purposes, this reaction has what I would consider poor regioselectivity. So there is some regioselectivity, but it's not very great whatsoever. Now, bromine, or so bromination, is much better in terms of regioselectivity. So if I were to look at those 2 reactions that I looked at with chlorine, so the reaction of bromine, or excuse me, the reaction of butane with a halogen, and the reaction of 2-methylpropane with a halogen, I see I get very different product distributions. So here I've drawn out the reaction of butane with bromine. So relatively similar conditions. Obviously, you see a much higher temperature, and that's because bromine has a little bit stronger bond, so I have to add a little bit more energy to get dissociation to occur. But when I get this reaction to take place, notice I get very little of that primary alkyl bromide produced, and I get a lot of secondary bromide. Right? So this would be, for synthetic purposes, a very good way of producing 2-bromobutane, right? 98% yield's pretty good, and that 2%, you know, I could probably get rid of in terms of, you know, working it up and purifying it. Likewise, if I take 2-methylpropane, react it with bromine, I see only the production of that 2-bromo-2-methylpropane, right? So 100% yield. And notice there is absolutely none of the primary alkyl bromide that's formed. Now, the reason for this, and if we went through that, you know, use that the equation that we used, we would see that bromine prefers a tertiary hydrogen 16, it says 16, but it's actually 1,600 times more than a primary hydrogen. So 1,600 more times than a primary hydrogen. And this is wonderful, right, in terms of thinking about synthesis, right, and getting a very high yield. So, as an example, I can take methyl cyclohexane, right, where I have a primary hydrogen, I have a series of secondary hydrogens, but then I have one tertiary hydrogen. And when I brominate this in the presence of light, I get essentially one product, right? And so this is, you know, good to know in terms of our synthetic toolbox.